Hello everyone, I'm Fabio Vito, and I would like to thank the organizers for giving me the opportunity to present X-ray Chandra observations of a redshift 4 gas-rich and star-forming protocluster, and about the discovery of a luminous Compton-thick AGN, which is powering a nearby lemon alpha blob in the structure. So just to put this into context, the AGN content in clusters and protoclusters has been found to evolve with redshift. In particular, in the local universe, people usually found a lower fraction of AGNs in clusters than in field environment, but this fraction is found to increase at higher redshift. For instance, at intermediate redshift, or redshift of 1, we see kind of the same fraction of AGNs in the clusters than the field. The situation is not so clear at higher redshift, but usually in protoclusters, redshift higher than 2, we see an enhanced AGN activity. So why is that? The basic and probably naive idea is that at higher redshift, underealized and overdense regions are more gas-rich, and also we have also higher rates of galaxy interaction and mergers. These two properties basically can help trigger supermassive black hole accretion and so AGN activity. Recently, some millimeter observations has been used to select high redshift overdensities of dusty star-forming galaxies, and I'm going to talk in particular about one protocluster, the distant red 4, DRC, a redshift of 4. It was selected as an overdensity of dusty star-forming galaxies with La Boca and ALMA at different frequencies. In particular, there are at least 13 spectroscopically identified dusty star-forming galaxies at redshift 4. All of them are actively star-forming with a total star formation rate, which is very high, higher than 7,000 solar masses per year. Also, the total gas mass has been estimated to be very high. For instance, the total molecular gas mass is in excess of 10 to the 12 solar masses. And this protocluster is a likely progenitor of a comet-like cluster or even more massive. You can find more information if you want in this list of papers. HST observations are available for DRC. In particular, HST revealed that most of the sub-millimeter sources are actually resolved into multiple interacting galaxies. So we do see a high rate of galaxy merger, galaxy interaction in DRC. We also have the MUSE observations, and MUSE detected a lemon alpha blob in the structure, in the protocluster. Lemon alpha blobs are usually considered as signposts of large reservoirs of cold and neutral gas, which is ionized by some power, source of power. This source of power has been often identified with obscured AGNs, nearby obscured AGNs. So just to summarize, in DRC, we have a lot of gas, so a lot of fuel for the AGN. We have galaxy interaction, ongoing galaxy interaction, so kind of these two properties basically can help trigger supermassive black hole accretion. And we also have a lemon alpha blob, which often has been associated with a nearby AGN. So we asked ourselves, what is the AGN content of DRC? And we obtained Chandra observation 142 seconds to detect X-ray sources in this protocluster. So this is the Chandra image of the core of the protocluster. In the full band, 0.5 to 7 kV. In green, I show the ALMA contours of the members of the protoclusters, and in cyan, the contours of the lemon alpha blob. So with Chandra, we detected DRC-1. DRC-1 is the most gas-rich and star-forming member of the protocluster, and also high-resolution ALMA imaging revealed that this sub-millimeter source is actually composed by multiple clumps in interaction. The X-ray luminosity of DRC-1 is quite high, higher than 10 to the 44 eggs per second, and the X-ray source is also heavily obscured with a current density higher than 7 times 10 to the 23 over square centimeters. We also detected a very luminous X-ray source in DRC-2. DRC-2 is the second most gas-rich and star-forming member of the protocluster, and it's also an interacting system of multiple galaxies as revealed by HST. The X-ray luminosity of DRC is very, very high, about 3 times 10 to the 45 x per second. And this X-ray source is a Compton-thick candidate, so a current density higher than the Compton-thick limit, let's say 10 to the 24 over square centimeters. Previous radio observations revealed that another member of the protocluster, DRC-6, is an active galaxy, is a radio galaxy. So now we have 3 AGNs out of 13 members of the structure. So this means an AGN fraction of about 20%. This fraction is sort of comparable with what is seen for dusty star-forming galaxies, both in the field and in protocluster environments. So we don't really see a strong enhancement of AGN activity in this protocluster. However, it's very interesting to note that we detected X-ray sources in the 2 most gas-rich members of the structure, and both of them are also emerging systems. So we do see this link between the availability of gas, so the fuel for AGN activity, galaxy interaction, and triggering of AGNs. Moreover, other low luminosity AGNs can be hidden in the other members of the structure, and this is suggested by X-ray stacking analysis, with which we detected a faint X-ray signal coming from the other galaxies. Here I'm focusing on DRC-2. On the left, you can see the X-ray image. I zoom in into the X-ray image of DRC-2. Again, in green are the ALMA contours, and in blue, the laminar flow blob contours. So this source is very luminous and obscured. And I would like to compare this AGN with other populations of AGNs. So in the right panel, I'm plotting the X-ray luminosity versus the column density for optically selected quasars in blue and green, which are typically luminous, X-ray luminous sources and unobscured or mildly obscured. And also X-ray selected quasars in AGNs in gray, which are typically less luminous and more obscure. And I also added some dust obscure galaxies and some emitter galaxies in black. So the SE2 sits up here in the upper right corner of this plane, which means that this AGN is as luminous as optically selected quasars, but it's much more obscure. It is actually the most luminous obscured AGN ever found in the protocluster environment. So here on the left, again, is the X-ray emission from the SE2. And on the same scales on the right, I'm showing the HST image. So again, in green are the ALMA contours, now in purple, sorry, are the laminar flow blob contours. I also add the contours of the helium-2 emission line from MUSE. So this is a very faint emission because the AGN is obscure, but basically it's telling us where the optical position of the AGN is. And both the optical position and the X-ray position are consistent with this HST galaxy here. But we also see the other multiple components in the HST image, which are lightly interactive. So due to the proximity of this luminous AGN to the laminar flow blob, the SE2, so the AGN hosted by the SE2 is the most likely source of power for the laminar flow blob itself, probably through photoionization or resonance scattering. But we also propose a different mechanism, which is related to the presence of a massive dusty molecular outflow launched by the luminous AGN, which is impacting the external gas reservoir, produces shocks. So we have shock-induced ionization, and so we can see the extended laminar emission. Currently, this possibility is quite speculative, and we need new ALMA observations with a higher resolution to prove the existence of an extended component, which the outflow basically. However, we do have some pieces of evidence in favor for the existence of this outflow. For instance, the ALMA contours are elongated toward the laminar flow blob, as if there is some extended component in that direction. And moreover, the laminar flow blob itself is structured in velocity. So the core of the laminar flow blob is red shifted, and the external parts are blue shifted. So basically, we have a cocoon, as if something is mechanically pushing away the gas, something like an outflow gain. So I'm going to conclude here. We don't see a strong enhancement of AGN activity in the FC, although stacking analysis kind of suggests there are other low luminosity and possibly obscure AGNs in the other members of the structure. We detected in the X-rays the 2 most gas-rich and star-forming members of the protocluster, and both of them are interacting systems of multiple galaxies. So we do see this link between gas availability, galaxy interaction, and AGN activity. One of the 2 X-ray sources is actually a very luminous AGN, very obscure Compton-thick AGN. It is as luminous as the optically selected quasars, but it's much more obscured. And it's actually the most luminous AGN ever found in a protocluster environment. Moreover, this AGN is the likely powering source of the Lyman alpha blob, possibly through photoionization, but we also propose that the presence of an outflow, dusty outflow, can produce shock-induced ionization. And we need, if new ALMA observation confirm this result, confirm the existence of this outflow, we will be witnessing the early phases of the AGN feedback in the surrounding environment, which in the end will affect the overall evolution of the protocluster down to the local universe. And you can find more information in this paper if you want, or just ask me here on Slack. Thank you.